Welcome back to the deep dive. Today, we are getting incredibly specific. We're zeroing in on a certification that I think scares a lot of storage professionals. The D-PWF-DS-01. That's
hmm
the Dell PowerFlex Design exam. And we're not just talking about high-level concepts today. We're going to look at the actual questions you are likely to face, the answers you need to pick, and, most importantly, why those are the right answers.
Exactly. This isn't about memorizing a dumb sheet. I mean, if you try to just memorize this exam, you might pass, but you are going to struggle when you actually have to deploy the hardware in the real world.
Yeah.
The exam it's designed to test if you understand the philosophy of PowerFlex.
Yeah.
It wants to know if you can think like a systems architect.
And the stakes are high right out of the gate. And I was looking at the exam blueprint, and the weighting is just fascinating. You have your standard sections like assess customer requirements at 10%, define requirements at 26. Those are important, sure. But then you hit a wall.
The design section.
Design the solution. It's 48% of the exam. Nearly half your score comes down to whether you can take a set of constraints and, build a working architecture out of them.
Which makes total sense. You can assess requirements all day long, but if you can't translate that into a valid node configuration or a proper network layout, the whole project fails. That 48% is where the rubber meets the road.
So our strategy today is pretty simple. We are going to reverse engineer that design mindset. We've pulled 10 specific practice questions that cover the most critical parts of the exam. We're going to break them down, look at the options, and really pinpoint the logic.
Let's do it.
We're starting with architecture and scalability. This is the foundation. I mean, if you get this wrong, nothing else really matters. So picture yourself in the exam center. Question 1 pops up.
Okay, set the scene for me.
The scenario is this. You have a customer who is very, very specific about their resources. They have a massive compute farm. Their servers are powerful, they're underutilized, but they are running out of storage space. They need capacity, but they explicitly tell you, do not sell me more CPU power. I have enough.
Ah, a classic stranded resource problem.
Exactly. So the question asks, which deployment model allows a customer to scale compute and storage resources independently by placing them on separate physical nodes?
Right. This is asking you to choose the fundamental architecture type.
Your options are A, single-layer architecture, B, integrated rack architecture, C, hyper-converged architecture, or D, two-layer architecture.
This is a great place to start because it really differentiates PowerFlex from a lot of other solutions out there. If you look at option C, hyper-converged or HCI, that is the industry darling right now. And it's great for simplicity. You buy a box, it has CPU and disk. But what's the flaw in this specific scenario?
Well, if I buy an HCI node because I need disk space, I'm forced to pay for the CPU inside it, even if I don't need it at all.
Exactly. You are over-provisioning. You are literally wasting the customer's budget. HCI couples compute and storage together. The question is asking for independence.
Which points us directly to D, two-layer architecture.
Right. In a two-layer design, you have one set of servers that just run applications. Those are your compute nodes. And you have a completely different set of servers that just drives your storage nodes. They're connected over the network, but they are physically separate things.
So if the customer needs 500 terabytes of space but zero extra CPU, you just roll in a rack of storage nodes.
Precisely. You scale exactly what you need when you need it. That is the definition of independent scaling. So for question 1, lock in D.
All right, moving on to question 2. This pivots to a term we hear in every single marketing deck, scale out. But the exam wants to know if you understand what that actually means for performance.
It's a buzzword, yeah. But in PowerFlex, it is a mathematical promise.
The question is straightforward. In a PowerFlex design, what is a primary benefit of using a scale-out storage architecture?
Let's walk through the options here.
Option A says it reduces the number of physical switches. Option B says it provides linear increases in both performance and capacity as nodes are added. C is about mixing hardware brands. And D talks about eliminating management tools.
Okay, to answer this, you have to understand the bottleneck of traditional storage. In a standard storage array, you have a controller, the brain. You can add 100 shells of hard drives behind it, but all that data has to pass through that one controller.
So eventually the brain just gets overwhelmed, you add more drives, but the system actually gets slower because of the traffic jam at the controller.
Exactly. That is non-linear scaling. It's diminishing returns. PowerFlex is different because every single node you add brings its own resources. It brings its own CPU, its own RAM, its own bandwidth to the party.
So the answer has to be B. It provides linear increases in both performance and capacity.
And that word linear is so key. If one node gives you 100,000 IOPS, 2 nodes give you 200,000. 10 nodes give you a million. It is predictable. That is what an architect needs to see.
Okay, so linear is the key word for scale out. Got it. Let's move to segment 2, components and communication. We need to talk about how these nodes actually, talk to each other.
The nervous system of the cluster.
Question 3. This is all about cluster integrity. The scenario involves a standard 3-node metadata manager, or MDM, cluster. You have a primary MDM and a secondary MDM. But the question asks specifically about that third guy.
The quiet one in the corner.
The question, what is the specific role of the third node to ensure cluster integrity during a failure? The options are A, primary manager, B, standby manager, C, tiebreaker, or D, data server.
This question is all about avoiding the split-brain nightmare scenario.
Describe that nightmare for us.
Imagine your primary MDM and your secondary MDM lose network connectivity to each other. They're both still powered on, but they just can't talk. The secondary thinks the primary is dead, so it tries to take control. The primary knows it's alive, so it keeps control. Now you have two bosses issuing conflicting orders to the storage.
Oh, that sounds like it corrupts data instantly.
It destroys the cluster. So you need a way to decide who is right. You need a vote.
So the answer is C, tiebreaker.
Correct. The tiebreaker is a very lightweight service. It doesn't hold the heavy metadata map. It literally just exists to cast a deciding vote. If the primary can see the tiebreaker, it has 2 out of 3 votes, it wins. It maintains what we call quorum.
It's the referee.
Is the referee that prevents the split-brain scenario. Exactly.
Tiebreaker ensures quorum. Now let's look at the actual heavy lifting, the data traffic itself. Question 5. We have the storage data client, or SDC, on the compute side, and the storage data server, the SDS, on the storage side.
Client and server. Simple enough.
The question asks, how does the SDC interact with the various SDSs?
This is one of the most important core concepts in PowerFlex.
The options are A, connects to a single master server, B, manual configuration, C, uses a middleware proxy, or D, communicates with all servers in parallel.
If you look at options A and C, they both describe a bottleneck. A master server, or proxy, implies that all traffic has to go through some kind of gatekeeper.
Which would slow things down.
Drastically.
Yeah.
PowerFlex is designed to remove gatekeepers. The SDC, the client, has a map of the entire system. It knows exactly which hard drive on which server holds the block of data it needs. It doesn't ask permission. It just goes and gets it.
So it's talking to everyone at once.
Yes. If you have 100 storage nodes, your client essentially has 100 open lanes of traffic. So the answer is D. It communicates with all servers in parallel for distributed data access.
That explains the performance. No single point of congestion.
Exactly. Parallelism is the secret sauce.
Okay, let's shift gears to segment 3. Reliability and protection hierarchy. Speed is great, but if I lose the data, I'm fired.
Reliability is usually the first line item in any SLA, for sure.
Question 10 deals with the logical hierarchy. We need to know the biggest container. The question is, which logical entity provides the highest level of resource isolation and administrative boundaries?
Isolation is the real hint here.
Options. A, storage pool, B, protection domain, C, volume group, or D, replication set.
So think of this like building an apartment complex. You have individual units, you have floors, and you have entire buildings. A storage pool is like a floor. It groups a bunch of drives together. But if the building catches fire, the whole floor goes with it.
So we need the building.
The building is the protection domain. The answer is B.
Why is that the highest level?
Because nodes in protection domain A are completely unaware of nodes in protection domain B. They don't share power, they don't share data, they don't share rebuilding resources. It's a hard wall. If you have a catastrophic software failure in domain A, domain B is completely unaffected. It just keeps on running.
So if I'm hosting data for 2 competing companies, I'd put them in separate protection domains.
Exactly. Total administrative and resource isolation.
Okay, so protection domain is the logical boundary. But what about, physical disasters? Question 6 takes it a step further. It asks, which feature is specifically designed to protect against the loss of an entire hardware rack?
This is where people get confused. They often confuse protection domains with this next feature.
The options are A, storage pools, B, fault sets, C, protection domains, and D, snapshot policies.
We just established that protection domains are logical boundaries, but the system needs to know about the physical world. It needs to know that these 4 nodes are sitting in rack 1 and those 4 nodes are in rack 2.
Because if rack 1 loses power, all 4 of those nodes go down instantly.
Right. And if your primary data was on node 1 and your backup copy was on node 2, and they're both in rack 1,
Yeah.
you just lost your data.
Game over.
So the answer is B, fault sets. A fault set is just a label that tells the system, hey, these nodes share a physical risk. PowerFlex then uses that info to ensure that it never places the primary data and the replicate data in the same fault set.
So if rack A dies, the system guarantees the backup is sitting safe and sound in rack B.
Correct. Fault sets are your insurance policy against rack failure.
Let's move to segment 4, optimization and best practices. We've built the structure, we've secured it, now let's tune it. Question 8 is a very practical design question.
I see this one in the field all the time.
The question asks, when designing storage pools, what is a recommended best practice for physical drives within a single pool?
Ah, the kitchen sink approach.
Right. Option A says, use identical drive types and capacities. Option B says, mix different technologies to save money. And, option B sounds tempting for the budget.
It is a trap. Do not fall for it. The answer is, without a doubt, A, use identical drive types and capacities.
Why, though? If I have some old SSDs and some new NVMe drives, why can't I just mix them?
Because PowerFlex stripes data across every single drive in the pool. It treats them as a team. So if you have a Ferrari and a tractor on the same team, and they have to cross the finish line together, how fast does the whole team go?
As fast as the tractor.
Exactly. If you mix fast and slow drives, the system is constantly waiting on the slow ones. You introduce these awful latency tails. The performance becomes completely unpredictable.
And what about mixing sizes? A 2 terabyte drive and an 8 terabyte drive.
That messes up the distribution. The small drive fills up fast, and then the system has to stop writing to it, which unbalances the workload. You want homogeneity. Balance equals speed.
Stick to the recipe. Identical drives. Okay. Now, question 9. This is about the network. We know we have parallel traffic. We know it's fast. How do we optimize the packets themselves?
The plumbing of the solution.
The question asks, which networking configuration is recommended for PowerFlex data traffic to optimize performance?
Let's look at the options.
We have A, standard frames, C, disable virtual segments, D, enabling jumbo frames with a high packet size value.
If you are doing high-performance storage over Ethernet, the answer is almost always D, enabling jumbo frames.
Explain jumbo frames to me like I'm a junior admin. Why do they even matter?
Think about moving a house. You have 1,000 books to move. You could put each book in a separate envelope, write the address, lick the stamp, and mail it. That's a standard frame, like a 1500 MTU.
That is a lot of envelope licking.
That licking is your CPU. Every single packet has a header that the CPU has to process. It's an interrupt. If you use standard frames, the CPU spends half its life just opening envelopes.
And jumbo frames.
That's a moving box. You put 50 books in one box,
Yeah.
one address, one stamp. The CPU does 50 times less work for the exact same amount of data.
So we are just reducing CPU overhead.
Drastically, we are freeing up the CPU to do what we actually pay it for. Moving data, not processing headers.
So answer D, jumbo frames. High packet size, usually 9,000.
Correct.
We are in the home stretch now. Segment 5, management and compliance. You can design the perfect system, but someone has to actually operate it.
Day 2 operations. This is where the dream meets reality.
Question 4 asks about PowerFlex Manager. Is this just some monitoring tool? The question asks, what is the primary function of PowerFlex Manager when deployed as part of an appliance or rack solution?
Well, it does monitor, but that's not its primary value proposition.
Option A is automating deployment and lifecycle management activities. Option B is about providing an internet gateway.
The answer is absolutely A, and the key phrase there is lifecycle management, or LCM.
Why is LCM such a big deal for the exam?
Because in the old days, upgrading a storage cluster was a complete nightmare. You had to verify the firmware for the drive, then the network card, then the BIOS, then the OS. It took weekends. It was so prone to human error.
And if you missed one step, the node crashes.
Exactly. PowerFlex Manager automates that entire stack. It says, I know what this node needs. It puts it into maintenance mode, evacuates the data, patches everything, reboots it, and brings it back online. It turns a risky manual process into a button click.
It's the consistency engine.
It ensures that Node 1 looks exactly like Node 100.
Which leads us perfectly to the final question, question 7. How does the manager know what to install?
The source of truth.
The question asks, what is the purpose of the Release Certification Matrix, RCM?
The RCM. It sounds so bureaucratic, doesn't it?
It does. But option C says, To ensure tested compatibility between software and firmware versions.
And that is the answer. C.
Why is the RCM treated like a holy book in the PowerFlex world?
Because of the complexity we just talked about. You have
Wow.
hardware from different vendors, drivers from the OS, software from Dell. There are literally millions of possible combinations.
And most of them probably don't work well together.
Correct. The RCM is the specific validated list of combinations that Dell has physically tested in their labs. They have proven that this specific drive firmware works with this specific adapter driver.
So if the RCM says use version 1.2 and you see a newer version 1.3 on the website.
You ignore 1.3, you use 1.2.
Yeah.
The RCM is your shield against instability. If you deviate from the RCM, you are basically becoming a beta tester for your own company.
And nobody wants to be a beta tester with production data.
Never.
Well, there you have it. That is your deep dive into the D-PWF-DS-01. We hope this helps you decode the questions and, more importantly, design better storage solutions.
Good luck with the exam. Read the questions carefully.
Thanks for listening. We'll see you in the next deep dive.